Good morning, students. Myself, Vijay Shankar from ECE Department, Chipoli College. Today, I are going to discuss about the Smith charts in the transmission line 2. In the last class, we discussed about the stubs and the lambda by 8th wave line and quarter wave line and half wave line impedances Zn is equal to with the length of transmission line, the lambda by 8, lambda by 4, and the lambda by 2, and also the single stub. Now I can go discussion about the Smith chart and how we can construct the Smith chart and what are the different types of stubs, single stub and the double. The Smith chart is a polar plot of reflection coefficient in terms of normalized impedance R plus Jx. So here the definition, the Smith chart. Smith chart is a polar plot of reflection coefficient in terms of normalized impedance R plus Jx. Or a Smith chart is a graphical plot of normalized resistance and the reactance in the reflection coefficient plane. See in the x-axis, the reflection R and the reflection I, the real term and the imaginary term, can magnitude of the reflection coefficient, and it is a 0. And we can draw a circle if the S is equal to 1. Okay. And when the reflection coefficient is equal to 1, the S is equal to the infinite. There is the ranges of the reflection coefficient and the S circles. S is equal to 1. Here the S is equal to infinite when the reflection coefficient is equal to 1 and the reflection coefficient is equal to 0. We already know the range of the reflection coefficient and with the range of the standing wave ratio, S is equal to 1 to infinite. It consists of two sets of orthogonal circles which represents the values of normalized impedance. It consists of two sets of orthogonal circles which represents the value of normalized impedance. One set of circles represents a resistive component R called as R circles, and other set of circles represents the reactive components X called as X circles. Okay, in this Smith chart we have the X circles and R circles. R circles called as a resistive components and X circles called as a reactive components. The Smith chart can be used to, these are the applications of the Smith chart. It is used to find the parameters of mismatched transmission lines and find the normalized impedance from normalized admittance. The first of all, you can find the admittance, then you can find the normalized impedance. Is 2 or the vice versa. Z is equal to 1 pi pi. Z is the impedance and Y is the admittance. For normalized admittance from normalized impedance also the vice versa. From normalized impedance from find the normalized impedance from normalized admittance and find the normalized admittance from normalized impedance. And also you can find the voltage standing wave ratio for a given load impedance. And fifth one is design the stubs for impedance matchings, find the reflection coefficient. So all the 6 applications you have to find in the Smith chart. Okay, we have to find the parameters of the mismatched transmission lines, impedance and admittance and voltage standing wave ratio, and also the design of the stubs, and finally can find the reflection coefficient. Okay. See, what is a stub matching? Next one is what is a stub matching? A stub is a piece of transmission line. A stub is a piece of transmission line. It can be short circuited or open circuited at the load end. Nothing but it is a far end. A stub is a piece of transmission line let us see, it look like whenever the transmission line is like this. A piece of transmission line, it can be short circuited or it is a open circuit. And if it is a short circuited, look like this, or it is a open line. It's a single stub. And if it is a double stub, we have like this. A piece of transmission line can be short circuited or open circuited at the load end. Okay. Now, stub has a pure reactance or susceptance. It is used to cancel out the reactance and susceptance of a transmission line. A stub is used for impedance matching. In the yesterday's class, nothing but is the last class, we already know the Z lambda by 4 is a impedance matching. Lambda by 4 is an impedance matching. You have to use a stub is used for impedance matching when a ultra high frequency line is terminated with a load impedance which is not equal to the characteristic impedance. If so, a mismatch is occurs. See, when we have it is a mismatch is occurs, then we can match the impedance. Means when a ultra high frequency line is terminated with a load impedance which is not equal to the characteristic impedance, which is not equal to the characteristic impedance, so a mismatch is occurs. This mismatch is reduces efficiency and the increase of the power loss. It reduces the efficiency and also increases the power loss. To avoid this mismatching, due to there is a loss occurs that is in terms of the powers and efficiency also. So power is increases here, increases the power loss and reduces the efficiency. To avoid the mismatching, we have to add the impedance matching devices between the load and the line. Nothing but it's just stubs. Okay. Once again, I will explain here, my students, why the mismatch is occurs. The stubs is always used in the mismatch impedance matching, and that mismatching occurs when there is a ultra high frequency line is terminated with the load impedance which is not equal to the characteristic impedance. So mismatch is occurs. Mismatch reduces the efficiency and also increases the power loss. To avoid this mismatching, we have to add the impedance matching devices between the load and the line. Okay, my dear students. Advantages. The length and the characteristic impedance of a line will be same. The length and the characteristic impedance of the line will be the same. Since the stub is added in the shunt, there is no need to cut the line. The susceptance or the reactance of stub can be adjusted for perfect matching. And methods of stub set matching. These are advantages, 3 advantages. The length and the characteristic impedance of line will be the same. See, whenever there is a piece of transmission line, you can add for the load and the line. That length and its a characteristic impedance of line will be the same. And since the stub is added in the shunt, there is no need to cut off the line. And susceptance and the reactance of stub can be adjusted for the perfect matching. Thereby, it is increases the power loss, decreases its power loss, and also the efficiency is also increases. There's a 2 types of stub matchings. That is a single stub matching and a double stub matching. Single stub matching. In this method, to achieve the impedance matching, an open or short circuited transmission line stub is connected in parallel to the main line. In parallel to the main line at a certain distance from the load. See, I already draw the single stub from the load end. This is a load end. Load end is a sending end of the transmission line. See, in this method, to achieve the impedance matching, an open or short circuited length of the transmission line is connected in parallel to the main line at a certain distance. This is a distance we have. This is a certain distance from the load end. Since the stub is connected in parallel, it is easy to use admittance for analysis instead of impedance. Okay. Since the stub is connected in the parallel, it is easy to use the admittance for analysis and instead of impedance. When the load impedance YR is equal to 1 by ZR, Z is nothing but the impedance and Y is nothing but the admittance. It is connected to the line. And if it is not equal to the characteristic impedance, Y naught is equal to 1 by the Z naught. That is, YR is not equal to the Y naught. The mismatching occurs. Got it, my dear students? This is an input end and this one is the output end, load end. ZR. In the load end, Z naught is a sending end and ZR is a load end. And these two are not equal. When the load impedance is connected to the line, if it is not equal to the characteristic impedance Z naught, YR is not equal to the Y naught, there is a mismatching of this. Okay. So the standing wave exists. So the standing waves exist on the line. The construction of the single stub matching is shown in the below here. The stub distance and the stub length and the load end, the YR is equal to 1 by ZR, and the source or the sending end Y naught is equal to 1 by Z naught, the single stub, the length of the stub, and you can place parallelly the single stub with the distance of LS from the load end. Okay. LT is the stub length and LS is the stub distance. When we move from the load to the source, the impedance on the line varies from maximum to the minimum, or it is a minimum to the maximum value, depends upon the length of the line. So what is the length of the line here? When we move from the load to the source, the impedance on the line varies from maximum to the minimum or the minimum to the maximum. The length of the line, you see, impedance matching occurs when we can take the length is a lambda by 4. Okay, like that is a total, the length of the, depends upon the length of this transmission line. From the load to the source, the impedance of the line varies from maximum to the minimum or minimum to the maximum. At some point on the line, the real part of impedance Y is equal to the characteristic impedance Y naught. Okay, when we move from the load to the source, at some point on the line, the real part of the impedance Y is equal to the characteristic impedance. When we can get the mismatching occurs is both are not equal. When both are equal, and the real part of Y is equal to the real part of the YR, sorry, my dear students, here it is a YR. The real part of the YR is equal to the real part of the Y naught. Generally, a short circuit is preferred than the open circuit stub because the short circuit stubs provides strong and support to construction on the main line. The short circuit stubs easily established with the metal plates, and the radiation loss is very less compared to the open stubs. Okay, and whatever here is showing that is a short circuited stubs only, not the open circuited. In the short circuited stubs, there is some advantages of the short circuited stubs. There is a radiation loss is very less, and compared to the open circuited, and it is easy to establish with the metal plates also. And disadvantages, the location and the length of the single stub depends upon the frequencies. If the frequency of waves changes, the length and the location of the stubs should be changed. It is very difficult to place the stub on a coaxial cables. These are the disadvantages when we keep the from load end to the length. stubs, double stub matching. Here there is a distance of stub 1 and the distance of stub 2. Let us assume from the load end to the main line it is a LS1 and LS2, and the length of the stub is a LT1 and the LT2. See, to overcome the disadvantage of the single stub matching, two stubs can be used for the different locations. What is a disadvantage here? The location and the length of the single stub matching depending on the frequencies. If the frequency of wave changes, the length and the location of the stub should also be changed. Okay. When the wave frequency changes, the length from the load to the length of the stub also have to change. That is a disadvantage. To overcome that disadvantage, we are going for the double stubs. Okay. With the distance of LS2 from the load end. To overcome the disadvantage of the single stub matching, two stubs can be used for at the different locations. This is called double stub matching. This is called double stub matching. Consider a double stub matching system consists of two short circuited stubs connected in parallel to the line nearer to the load. Nearer to the load. The characteristic impedance, not the impedance, sorry, the characteristic admittance of stubs should be equal to the characteristics admittance of the line. So Y is equal to Y naught. In this system, the locations of stubs have to chosen arbitrarily, but it is very difficult to design the stub matching with arbitrary locations. So the locations of stubs should be restricted. The admittance repeats at every lambda by 2 the length. Okay, the lambda is here. There is a 750 degrees in the Smith charts. It is not in the when the designing of the any stub lengths. The characteristic in this system, the locations of the stubs have to choose an arbitrarily, but it is very difficult to design the stub matching with arbitrary locations. So the locations of stubs should be restricted. The admittance repeats at every lambda by 2 length. The total distance nearby the more than or equal to the lambda by 2, that is LS1 plus LS2. Both the E2 combination is less than the lambda by 2. LS1 is in between of 0.1 to the 0.15 the lambda. So sometimes it is LS1 is equal to the 0 also from the load end and chosen. The space between the two stubs is generally taken as lambda by 8, lambda by 4 or 3 lambda by 8 distance. The lambda by 4 is using for the impedance matching. From the load end only, my dear students. The total distance of double stub matching should be small, and the double stub matching consists of fixed stub locations. The impedance matching is done by finding the length of the stubs. Okay. And there is a transmission line losses. The losses in the transmission lines are the 3 types. These are copper losses, dielectric losses, and radiation losses. The copper losses occurs due to I square or the power loss and the skin effect or crystallization. I square or the power loss due to the dissipation of heat in pure resistance. Skin effect is used to an AC signal at the high frequency applied to the transmission line. The current is restricted to the surface of the conductor. And these are all the points where we have the losses occurs in the transmission line. That is the copper losses, dielectric losses also. The dielectric losses due to the improper characteristics of the dielectric, and the radiation loss. These radiation losses due to when the spacing between the lines is high. The spacing between the lines is high. At high frequencies, lambda will be the small, and hence the transmission lines are not useful for the high frequencies. These are the losses in the transmission lines. These 3 losses are the copper losses, dielectric losses, and the radiation losses. And the lossless radio frequency transmission line, we already know that R is very much less than the omega L and G is very much less than the omega C, and Z is approximately equal to the J omega L because it is R is neglecting, and here the admittance Y, the G is neglecting, the Y is J omega C, and the characteristic impedance we know under root of R plus J omega L by the G omega C. The characteristic impedance is under root of L by the C. And the propagation constant also, the gamma is equal to, it's not the gamma, I explained in the P is equal. Okay, you can write the gamma or it is a P. The P is equal to under root of R plus J omega L and G plus J omega C. The lossless is under root of R is neglecting the J omega L and G is eliminating or neglecting J omega C in the radio frequencies. J omega will be getting its under root is a J omega and root LC. The gamma is equal to nothing but the propagation constants. Gamma is equal to J omega root LC. By comparing the real and the imaginary part, alpha is equal to 0, the attenuation constant is 0, means it's a lossless. Beta is equal to omega root LC, the phase constant, a radians per meter, and attenuation constant is a Napier's per meter. We already the phase velocity is omega by beta, or it is a 1 by root LC. Now we go to the construction of the Smith chart. The construction of a Smith chart, we know the Smith chart is defined as a polar plot of the reflection coefficient in terms of normalized impedance R plus J omega Jx, not the J omega, R plus Jx, where R is a resistance and X is a reactance. The Smith chart is graphical plot of normalized resistance and the reactance in the reflection coefficient plane. One circle is R circle, resistive component R is called R circles, and other set of the circles represent the reactive components X called as X circles. So the construction, the Smith chart is constructed with a circle of unit radius. The reflection coefficient is very much less than, not the less than or equal to the 1 as shown in the given figure. You see here, less than the 1, the circle S is equal to 1. And the reflection coefficient is equal to ZR minus Z0 by ZR plus Z0. This is the equation we already derived. The reflection coefficient is equal to ZR minus Z0 by the ZR plus Z0. When we can write the reflection coefficient in terms of the polar form, the magnitude of the reflection coefficient and with an angle theta R reflection coefficient, it is a theta R. Its magnitude is depends upon when the theta is reflection coefficient is equal to 0, at that the S is equal to 1, and the reflection coefficient is equal to 1, the S is equal to infinite. And in the rectangular form, the real part of the reflection coefficient plus J into the imaginary part of the reflection coefficient, where here see the real and the imaginary part of the reflection coefficients, gamma R and the gamma I. For load impedance, ZR is equal to the normalized load impedance is given by ZR is equal to, this is a normalized impedance minus. So this is representing as a Zn. Zn is equal to the normalized load impedance, Zn is equal to, or ZR is equal to, see the normalized impedance, ZR by the Z0. Okay. Actually, is a small z when we can represent ZR, normalized impedance, and ZR by the Z0 in the reflection coefficient. So the reflection coefficient, we know ZR minus Z0 by the ZR plus Z0. Take the Z0 is a common. ZR by the Z0 minus 1 by ZR by Z0 plus 1. And Z0 get cancelled. And you can replace ZR by the Z0 is nothing but the normalized load impedance Zn, or it is a Zr. In some textbooks that is representing as Zr, and it depends upon there is a confusion between of Zr and here the Zr. You can write this as a Zn. Okay, for our convenience. Got it, my dear students? So Zn minus 1 by the Zn plus 1 is equal to the real part of the reflection coefficient and the imaginary part of the reflection coefficient. Got it? Now, cross multiplying the function Zn plus 1 into gamma r plus j into gamma I is equal to Zn minus 1. So multiply these two functions Zr, and now we got it is a Z Zn minus 1 is equal to, multiplying that, it is a gamma r Zn plus gamma r. Then you can multiply with the imaginary coefficient gamma I into Zn plus j into gamma I. Okay. Bring all the Zn terms in the left hand side. Zn you can take as a common 1. You get this one is to here towards the left side. Gamma r minus, and here the Zn coefficient is a j into gamma I is equal to, what is the remaining part here? Gamma r plus j into gamma I, and here the minus 1 you can get in the right hand side, it will be the plus 1. So the normalized impedance of Zn is equal to, that is a Zr by the Z0. Now the gamma r plus j into gamma I plus 1 whole divided by, and 1 minus gamma r minus j into gamma I. And in the numerator also you can change that as 1 plus gamma r real part plus j into gamma I whole divided by 1 minus gamma r minus j into gamma I. Okay. Then what is the normalized impedance here? See, the multiplying and dividing the rationalized you can do, because the denominator is a 1 minus gamma r minus is there. You can multiply and divide with the 1 minus gamma r plus j into gamma I. That Zn is equal to, we are saying that in the switch chart there is a two circles. One circle is a resistive component R, another circle is the reactance component X. So then equate with the R plus Jx after rationalizing. You see, after rationalizing, the denominator becomes 1 minus gamma r minus j into gamma I, and plus a square minus b square, 1 minus gamma r square minus j square into gamma I square. And in the numerator, you can multiply all the terms. You'll get r plus jx is equal to, r plus jx is equal to, after simplifying 1 minus gamma r square here, the 1 minus gamma r square, and there is a 1 minus gamma I square, and the imaginary part j gamma I and j gamma I. So 2j gamma I here, and denominator 1 minus gamma r square whole square plus gamma I square. So normalizing and equating the real part and the imaginary part. The real part is r. Real part 1 minus gamma r square minus gamma I square by 1 minus gamma r square plus gamma I square, and the x component nothing but the reactance component x circles 2 gamma I by the 1 minus gamma r square plus gamma I square. Rearranging the above equations, then we get and gamma r is equal to, in terms of the gamma r minus the term and gamma I minus term, nothing but A and B, and here the R square. And similarly here also the gamma R minus A and gamma I minus B is equal to R square. The R circle and the X circles. The above equations we can take it is as X minus H and K. Here they are assuming that X minus H and Y minus K. A square, where A is the radius. And in the R circle also, as in the R circle, the resistance circle, what is a H and what is a K? R is equal to H is equal to R by 1 plus R and K is equal to 0. Okay, and you have to derive these expressions also how we get. Okay, my dear students.